So let's start. So today I am going to quickly review some basics of cryptography, right? Because I don't know, do you guys already know crypto? Have you taken a course? Okay, good. So if it's, I'm going to go very slow, but if it's still something is not clear, you can always stop me and ask. Okay. So I'm not going to give you a proper full introduction. I'll only give you the material that's needed for understanding the paper that we were looking at, and then afterwards I'll fill in the remaining details. Okay. So we're going to start with basically secret, or just, let's see, what I want to call it. I want to call it, yeah, so let's just say symmetric key encryption. That's what we're looking at. Symmetric key, it's also sometimes called secret key or private key. Private key encryption. Okay. You can read, right? It's, the font is good. Okay. So what is the setup here that we're looking at? The setup is very standard. It's one of the older setups, right? So there's Alice, there's Bob, and they want to exchange information on some public channel. So there's a public channel. So by a public channel, I mean it's accessible to everyone, right? And they want to make sure that nobody who is listening in on the public channel is able to recover the messages. Okay, so this is what we want to do. So typically, the way we define, actually, you know what? Maybe give me a second. So the way we define such an encryption scheme is following using the following syntax. So there's going to be what is called a key generation algorithm. Okay. So this will basically tell you how to pick some key k using this generation algorithm. Okay. The second is called an encryption algorithm. Yeah.
Can you make the font a little bit bigger?
Yeah. The second one is. Okay, so the second one is the encryption algorithm. And what this is going to do is it's going to take the key k. It will take some message m, okay, and it will produce a ciphertext C. Okay, that's the syntax. And then there's a decryption algorithm. Which takes as input a ciphertext. Right, decryption K. It takes as input a ciphertext and produces, well, gives you the message M. Okay. So I'll state it again slightly later, but this arrow notation here is basically referring to the fact that this is a randomized procedure, okay, and the output is given by k. So it's one instance. If you run gen again, you'll get potentially a different k. Okay, that's what the arrow means. Similarly here, when you encrypt something, you potentially get different ciphertexts, even if you run it again on the same input. But decrypt, we want it to be deterministic, right? So because given a ciphertext, we want it to produce the same message every time you decrypt it. Okay, so that's just some notation. And what do we want? We want, correctness is kind of clear, right? So the correctness property that we want is that
even if k is fixed there, the C can be different.
Yeah. That's the whole point. It's randomized. Okay. Yeah. Exactly. Just like here, right? So gen has no input, but it's still producing a different k every time. So it's randomized. So there's some internal randomness in the algorithm, which I'm not writing explicitly. Yeah. Okay. And then there's correctness. So the correctness condition is what? The correctness is that when you run decrypt on the encryption of some message, can you actually read or is it too high? It's too high, right? There's a shadow. Yeah.
It will be better if you write down for your own recording.
Yeah. Okay. Oh, okay. Thank you. Makes more sense. Okay. So correctness the correctness condition is that you decrypt the message, you encrypt the message. Sorry, the other way, you encrypt a message and then you decrypt it, and then this should give you the same message back, right? So that's the correctness condition, so nothing very complicated so far. But now there's like a little bit of a conceptual discussion, so let's have that. So clearly, we want to keep the secret key secret, right? So Alice and Bob should have access to K, right? So they somehow meet at some point, they exchange the key, right? And nobody else has access to K, right? Because obviously it's a secret key. That's the entire setup. So what do we want to keep secret, right? So we do want to keep the key secret, right? Somebody had suggested last time, and it's maybe not evident the first time you look at it, is whether we want to keep the description of the algorithms also secret. Okay, so do we? So this we do, right? And the question is, do you keep gen, enc, and dec also secret? Okay, and it turns out that it's not a good idea to keep these secret, to keep the algorithm secret, and there are a few reasons for this. So this was first pointed out by this person called August Kirchhoff, so in the 19th century. So this is like story time now. So story, 19th century. Kirchhoff. So I'm writing it so you can look it up later. Hey, Kirchhoff. So he pointed out that basically the same field. So there's the security. So he said security should rely solely on the secrecy of the key. Should rely solely, I'll put it in quotes for now, solely on the secrecy of the key. Okay. And why is that, right? So why do you think that's a good idea, or why do we think that's a good idea? So the first is, so why, right? So the first argument is that it's easier to maintain secrecy of a small key. So easier to maintain of a small key, right, compared to the description of the algorithm, which could be much more involved. But more crucially, it's possible that details of the algorithm or some detail of the algorithm gets leaked. Okay, and what that means is that you can no longer use the scheme at all. In contrast, if some detail of the key was leaked, you could throw that key away and use a different key, and you're still secure. Okay, so you will not have that property if the secrecy depends on the secrecy of the algorithm itself. Okay, and there are a bunch of advantages, right? So first is that so that's one part. The third is that you can have a public scrutiny of the algorithms. So different scrutiny. So you can have white hackers, as they're called, or ethical hackers, maybe that's a better term. So you have ethical hackers, right, that can tell you what the vulnerabilities in the system are and so on, assuming that you have the algorithms available public. Also allows you to standardize things, right, which is very helpful. Okay. And historically, often people have tried to rely on the secrecy of the encryption scheme, and it often gets leaked, and then it compromises security. So it's always good practice, and this is what all of modern cryptography assumes, is that the description of the algorithms is publicly available. Okay, good. So this is what I wanted to say about just the idea of what we're going to keep secret. The last thing I wanted to mention was the different kinds of attacks that we'll consider. Okay. So so here's a list of attacks that we'll consider. Okay. So we're going to consider what are called ciphertext-only attacks. Okay, so here what happens is you get one ciphertext, okay, and you want to figure out what the message is. So this is a ciphertext only attack. So we're assuming that's all the adversary wants to do. He somehow found one message encrypted using your scheme, and he wants to recover what the message was. The second is called a known plain text attack. Okay, so here the adversary gets a bunch of ciphertext. So here the adversary had only one ciphertext that he wanted to recover from. Here there can be many ciphertexts that somehow, so for example, he was just sitting on that public channel and he received many ciphertexts while you were communicating, and then he has a collection of these ciphertexts that he wants to use to break one specific ciphertext. Okay, so this is so I'm giving you successively more powerful attack models.
If we have plain text also corresponding to the encrypted text.
Yeah, we assume that here, that you have a pair of the plain text and ciphertext, and then there's a new ciphertext for which you do not know the plain text and you want to find it out. Okay. Yeah, thank you for that question. I didn't say it clearly. Okay, then there's something called the chosen plain text attack. Okay. So here what we do is we allow the adversary to pick a sequence of messages which could be different from which are going to be different from the message he's trying to decrypt. So there's a ciphertext C that he wants to decrypt, and there are a bunch of messages, let's say L, for which the adversary can ask encryptions of. So he can ask that what does M1 encrypt to? It's the encryption key of M1 and so on. Okay, so he can ask for encryptions of a sequence of messages that he likes. Okay, and then given this, he has to recover the message corresponding to the ciphertext C. Okay, so this is an even more powerful model of an adversary. And one way to think about it is that imagine you're in some kind of a, suppose that these guys are battleships, and you're somehow able to scare one of the battleships into communicating with the other battleship, right? So then you can somehow force them to start sending messages about which you might know what the content is. And so that's the kind of things this is capturing. And the final one is called, which is the most advanced one, this is called the chosen ciphertext. So chosen ciphertext attack. Okay, and here what one is doing is one not only is allowed to do this ask for encryptions, one is also allowed to ask for decryptions. So one can just come up with a bunch of ciphertexts, say C1 to CK. So C is the one that they want to decrypt. They can ask for decryptions of C1 to CK, which are none of them are C, so they're all distinct from C, and they will get decryptions. So they'll get M1 to MK, which are decryptions of C1 to CK. Okay. And the claim is that as long as these are distinct from C, they should not be able to recover the message. Okay, so these are kind of the four attack models that we're going to consider in what follows. Okay, good. By the way, everything I'm telling you is from this book called Katz and Lindell, and it's very nicely written. So it's very easy to follow. So you're welcome to take a look at it if something is not clear, or if you want to read further. Katz and Lindell. I forget if it's a double L or a single L, but something like that. Okay, good. Okay, so that's kind of the setup. Now let's look at what are called the basic principles, in the text at least. Basic principles of modern crypto. Okay, so there are basically two principles that we're going to look at. The first is formalizing the security definition. Okay, and this is the thing that we were trying to do yesterday, but it wasn't quite clear what was happening to some of us because we'd not seen how it's done in simpler settings. So we're going to do that now. So the basic principle is to first have a mathematical and formal definition that captures the notion of security that we want intuitively to hold, and then we want to give constructions satisfying this definition. Okay, construction satisfying this definition. Okay, so far it's obvious, right, that you would want to do this. But the issue that often arises is that it's impossible to satisfy the definition without making additional assumptions. Okay, and so if you have to make additional assumptions, what we want is to show that the definition can be satisfied by okay, let me phrase it another way. We only want to make simple, precise assumptions. Okay, and we want to show that as long as that simple, precise assumption is true, our construction is satisfying the definition. Okay, this is what we want. So we want to basically show definition. So okay, if assumptions are needed, of course, if you can do it without assumptions, it's great. But if assumptions are needed, okay, then we want the assumptions to be simple and precise assumptions. Simple and precise assumptions. And B, we want to show that assuming A holds, so assuming A holds, we want to show that one is satisfied. Okay, so this is going to be the general paradigm in all of.
What choosing plain text stack? If you have, say you have like the box or the machine that will like encrypt the messages, and then you can just feed in whatever message you want. So that kind of makes sense. But then for like chosen ciphertext attack, how do you enforce that like CI is not equal to C? Because if I have the decryption box, I can just give C.
Yeah. That's a good point. So the idea of giving an encryption box in CPA, chosen plain text attack, what that is doing is it's just a formalization of a physical situation. The physical situation being that you can sometimes sit on a channel and listen to things, or you can tell someone like you have some inside information, like some informer who can actually send ciphertext, give you a ciphertext for the message you want, and so on. So it's just capturing the most general way that could happen, which is to just say, look, you can encrypt any message you want, and even then it's secure. So it captures all of those situations. Obviously, here if you do not put this restriction, then it's meaningless, because then the notion of security doesn't make sense. Your question is, how do you in practice prevent the if I give you a decryption oracle, how do you prevent me from inputting the same ciphertext to get the thing? But that's the whole point. These are not how reality works. These are just formalizing how reality works. So it's not that you will ever have access to a decryption oracle, because if you did, then of course the encryption is broken. There's nothing to it. This is saying even if you had like somehow a physical situation where you could get infiltrate them, infiltrate the security system in a way that you can get decryptions, barring the fact that you can get a decryption of the ciphertext that you want, the thing is still secure. So that's all it is.
Ciphertext. Can you request can K be all the ciphertext except for C?
Yeah, so the space of ciphertext is typically going to be exponential, and you're going to assume that you're polynomial, and all of these things will come. Yeah. So you cannot exhaust all ciphertext. Yeah. Okay. Any more questions? Okay. Wait, where was I? Oh yeah, here. Okay, so that's the basic paradigm we're going to assume. Okay, so let's do a little exercise and try to figure out what the security definition should be for the encryption scheme that I had listed earlier, the secret key encryption scheme. Okay, so to this end, so let's look at an example. So this is okay. So let's try to apply principle 1. So principle 1. Here's an example. we're going to apply it to symmetric key. Symmetric key encryption. Okay, so what is the example? Yeah, so how do you want to define the notion of security? So I'll give you one, which is not going to be the best notion, and then we're going to successively make it better and see how it proceeds, okay? So often if you ask people what the notion of security should be, one of the answers that you might get is that no adversary should be able to recover the secret key from the ciphertext. Okay. Clearly, because if they could recover the secret key, then the encryption scheme is broken. This is kind of clear. But the question is this a reasonable notion? Can you think of an encryption scheme which would satisfy this property, which would immediately satisfy this property and nonetheless would be completely insecure?
Addition to modulo.
Okay. So what do you want me to do? So I have a message M.
Yeah, and then you can add like secret key.
The ciphertext is M modulo K.
Okay. Yeah, let me just write it as K. That's better because that's the notation I was using. Yeah. Uh-huh.
And then like it could be on like, or if you're taking bits, it could be like modulo 2.
Yeah. Sure.
And similarly we decrypt
Sure.
E being K.
No. I was asking something else. I was asking what you're describing seems to be a scheme that is secure, which satisfies this definition. I was saying, can you come up with a scheme which is completely broken and nonetheless satisfies this definition?
Yeah, but like if
This
we
is
have-
not broken, right?
If we have two ciphertexts.
No, this is a single ciphertext. We're in this software. Sorry, I should have mentioned. We're looking at this model.
Okay.
Yeah, of course, yeah. Otherwise, you can start playing it. Yeah, sure. Okay.
You can guess.
Huh?
You can guess the key.
Yeah, but that's just random. See, I want you to do better than random. That you can anyway do. You can just guess the message, right, with that probability. So it doesn't help. Okay. So here's a very dumb encryption scheme, and I know this because I read. Okay, I'm not clever. I would also been stuck. But here's a very, very dumb scheme which is completely insecure, but which satisfies this definition. Okay, ready? Okay, here's the scheme. So the encryption K of a message M. Okay. Exactly. It's just the message M. Okay. Yeah? So you see it satisfies this definition because no information about K is being released. And it's manifestly insecure, right? You're leaking the message. So you have to be careful. So these definitions are more tricky in crypto, okay? So that's the first one. So the second one can say is that, so when people hear that, okay, look, obviously this thing doesn't work, the next thing you can say is that, you can say the same thing, then the no adversary should be able to recover the message M, right? Right, so this seems like a lot more reasonable. At least we're getting to the essence of the thing, that the secret key is not really the important thing.
So whenever we say no adversary, we mean like no body time adversary.
At this point, I've not done computational things, so we can think of it as unbounded if you want. Yeah, we'll formalize that later. I'm just building from like the basics, and then we'll build and get to the assumptions. Okay, so this looks like a reasonable notion, right? But this is also somehow lacking. Can you think of a scheme that would satisfy this, but would still not be secure intuitively?
Like if the ciphertext is only like random,
Uh-huh.
then you don't have a valid decryption algorithm.
Right. Yeah. So assume it decrypts correctly.
Oh, okay.
Assume it decrypts correctly. Yeah. That's a good point. Yeah. You could just give some randomness. Right? Say it's not correct at all. Yeah. You could do that. So okay. So maybe the wording is not clear, but intuitively, when we say the message M is not recovered, we're kind of Like, what do we think of a scheme that leaks 90% of the message?
Like all but one bit.
Yeah, for example, right? So this is saying you cannot recover M, right? So say M was like a 100-bit string, you leaked 99 bits. You still cannot say that it leaks M because that you learned the message M, because you still don't know, okay, 1 bit you can guess, maybe like say, there's half the bits you don't know. But you still wouldn't call it secure because you've leaked half the bits.
So when we say that no one should be able to recover either the message or key, we're saying like can recover with probability 1.
Yeah, sure. These are just illustrations, but yeah, sure. In my example, I was saying you could recover a set of bits. You could say that with some probability you could recover. Sure, you could do that. Yeah, we'll formalize those things in a little bit, but yeah, here the point was that we're just trying to see what the definition is, and I was just trying to say that these definitions are inadequate the way they are, because you could have the kind of scheme like you divide your message into 2 parts, so M0 and M1, right? And the encryption scheme only encrypts M0 and leaves M1 in the clear, right? So that scheme would not be secure. So what would be a better definition? So one can then say, okay, so recovering the entire message is not important, right? We don't even want nothing meaningful about M should come out of C. That's kind of what we want, right? So somehow no adversary should be able to get should be able to recover anything meaningful about M. Okay. But then again, it's not very clear what meaningful means, right? Because it could be in different contexts. Meaningful could mean different things. And so how that's formalized is that you should not be able to extract any function. Okay, so this is the final one. Did I skip one? Okay, I skipped one. There was one very interesting case in between that I accidentally missed. So before this, like you could say 2 prime, that you shouldn't learn any bit of M. Okay. You could say, for example, because like the example I gave was, you were learning some bits. You could say, you don't learn any bits. So you don't learn any bit of M. Okay. But you could still learn something like, so for example, if I had the encryption of somebody's salary, you could still learn whether it's greater than, I don't know, 5,000 or less than 5,000. Right. Sorry, I messed up. I should have done it properly. But
saying that you can't do better than guessing like the bit.
You can't do better than guessing the bit.
Like for all bits.
Yeah, of course. Like all of these things are, you can always randomly guess. I'm trying to say, can you do better than random guessing? Of course, yeah. Okay. So even just saying that, if I have a big message and I want to learn just parts of the message, that should be impossible. That is not enough because of the example I gave, right? Like if I give you somebody's salary, you might still be able to learn whether, you might not know what the exact value is, but you might still be able to learn which interval it lies in, for example. Okay? And that is still not secure. So what we really want is that nothing meaningful about M should be learnable from C. But then meaningful is not very clear, and how we formalize meaningful is that there should be no function of the message that you can recover from C, because that's how it's formalized. Okay. So 2 prime 3, and then let's just say 4, which is no function f of the message M should be computable from C. Okay. So all of this was just to impress upon you the fact that getting the security definition right, even though it sounds very simple, it's something you have to do carefully and you have to get it right. Okay? Okay, good. So that was the first principle. I am skipping some details, okay? The book has more details. I'm just giving you a very quick overview of things. So there's no substitute for that, but should be enough. Okay, so that was principle 1. I'm trying to decide how much detail I want to go in. Okay. So principle 2 is that
Function of message meaning like what? Like if I give any like the encryption protocol, like giving a message and getting a ciphertext. Here like no function of f, the message m should be computable.
yeah, you know the algorithm, but you don't know the secret key, right? So you can give the encryption algorithm, but since you don't know the secret key as an adversary, you will have to. You can give it some input of the secret key if you want. Like you could say encrypt with key 0 or decrypt with key 0 the message m. You should not be able to recover that information from the ciphertext. Yes. Maybe I misunderstood your question. What was your question?
Like no function of f of the message. So what function we are talking about?
Yeah, you want to prove this, that there's no function, irrespective of what f you choose, you should not be able to recover f of m from the ciphertext C. Like f of m could be like you give me the first bit, could be the second bit, or could be is this greater than 10, is it less than 10. So no possible function of m should you be able to recover from C, except of course a constant function, those things are trivial. But, yeah.
Like, this is kind of obvious, but formally I'm not getting the difference between algorithm and key, because any algorithm you could just write it using some Turing machine. And the
Sure,
Turing
sure.
machine will have some like description,
Sure.
like binary string description,
Sure.
and then this key will also have some binary string description.
Right.
So it's like keeping the key secret versus like keeping the algorithm secret. It doesn't.
Yeah. So there's always this distinction. I think the only thing that you're trying to say is that there would be some part of if you're thinking it abstractly, there would be some part of the key, some part of the string which would encode the algorithm, and some part that encodes the key. We just want to make sure that we only want to keep the part that's the key to be secret. That's all. Because you will use some procedure, right? It's just that you don't want the security to rely on the fact that the procedure is hidden from public view. Partly because you can then analyze, right? Like you can scrutinize the algorithm, right? Like people can check if there are vulnerabilities and so on. Which, abstractly, of course, they're equivalent. Like data and computation are equivalent. That's like the basics of Turing, right? Like that's the whole idea. But it's a good point. Yeah. Okay. So any more questions? Is everything good? Yeah.
3 and 4 are two different points, right?
Yeah. Because the notion of meaningful is not clear, right? Like what does meaningful mean? It's not a mathematical word. Like what do you mean by meaningful, right?
Do no better than guess the message.
That's number 1. No, you can't go backwards. You have to make it better.
No, number 1 is guessing the key.
Oh, sorry, number 2. One of them is guessing the message. Yeah, number 2. Sorry. Because then you have the same attack, right? Like I said, like you could learn like 80% of the message, and it would still satisfy security too, right? So you don't just want to say that I should be able to recover the full message. So then you can say maybe partial message should also not be recoverable, but that's also not enough, because maybe you could learn what interval the salary lies in. Maybe you don't know how much the salary is, but you can still learn. So you don't want anything meaningful about M to come out, but how do you formalize meaningful?
The formalization is
Yeah, formalization. Okay. All good? Yeah, it's good to be clear about these simple things. Okay, there's no real math, but it's just the way of thinking in crypto that's a bit important to spend some time on when you're new to it. Okay, so now here what we want to do is Okay, so why did we insist on precise assumptions, precise simple assumptions? Okay. So one reason is obviously the validity of the assumption itself. Right? Because
So back to what you were saying. So, like, if we can do no better than guessing the message on the full message space, then doesn't that mean it's secure? Like, doesn't that mean nothing meaningful is leaked?
In that case, we can think of this function maybe this function where given the ciphertext, the number of bits the message. That's some information about them. Maybe.
No, but that reduces your message space, right? If you know the number of bits of the message, then your message space reduces. So guessing in the entire message space seems to be like if the adversary can do nothing better than guessing in the entire message space, then it seems like it's secure.
yeah, so that's partially correct. It could be that somehow the adversary knows some information about the distribution of the messages. Say, for example, from counterintelligence, I know that there's a 70% chance you'll attack tomorrow and 30% you won't. And I have a ciphertext that I need to decrypt. So then your definition breaks down, right? Because you're assuming that the distribution is uniform over the messages a priori, which may not be. But you're close. Like the way you formalize it is basically saying that, and we'll do it in a moment, you formalize it by saying that you would have some a priori distribution over the messages, and you want it to be such, you want the encryption to be such that given the ciphertext, this distribution doesn't change. So it's formalized in a, you're on the right track, but just that you cannot assume that the distribution over the messages is uniform or whatever fixed thing. Yeah.
Sir, here we can consider I'm just asking do we consider the case wherein we have multiple ciphertexts?
Not yet. We'll do that later. Otherwise, yeah, you are the scheme that you had written would not be secure as well, right? Exactly. Okay. Right. So why do we want precise and simple assumptions? So the first is, of course, that we want the assumption to be true, and having simple and precise assumptions allow them to be studied, right? So you can gain some confidence in the validity of the assumption itself. Second is a comparison of schemes. So by this, what I mean is that you may have different encryption schemes using different assumptions, and you might know which assumptions are weaker and which are stronger. Right? So you want weaker assumptions. You want stronger assumptions, weaker assumptions. Weaker assumptions. You want weaker assumptions, so that they're more likely to be true because you're assuming less about the world, and ideally you don't want to assume anything about the world. So weaker assumptions are better, and this allows you to compare schemes. So there are two schemes that one of them performs slightly better, but it might have a stronger assumption than the other. So it gives you a systematic way of looking at which scheme is relevant to your application. And the third is facilitation of proof of security. Facilitation. How do you write facilitation? Facilitation. Okay. Of a proof of security. Okay, so this is essentially the same point that we had before, that you want to prove the security by reducing it to, I'll formalize what that means in just a second, this assumption that you've stated. Okay, so we want something along the lines, the construction is secure if assumption is true. Construction is secure if assumption is true. Okay. Okay, good. And how does one formalize this idea? How do you go about showing this, that the construction is secure if the assumption is true? You do the contrapositive, right? So basically you show that if there exists an attack on the construction, let's say. So what I mean by an attack, we'll formalize it properly later, but for the moment I'm just assuming that whatever definition you set out to satisfy, right? If you can show that there is an adversary that can, given your construction, violate that definition, then the assumption is false. The assumption is broken. Okay? So this is called the reductionist approach. Okay, we'll formalize it. I'm just giving you like a high level idea of how things are shown. Okay, good. Okay, so that was all that I wanted to say about the general paradigm, to emphasize on how we have to get the definitions right, and now we can actually apply these things properly to constructing secret encryptions without additional assumptions. So that's the plan. Okay, so let's do it. Let us start with, and the construction is essentially what you said. It's just the one-time pad. So we'll successively make it more involved. But let's just start there. Okay. So we have until 11:30, right? So okay, good. Okay, good. Okay, so now we're on. So if you want to look at the book, this is chapter 2 of the book. It's perfectly secure. Perfectly secret encryption. Okay. So okay, so it's given by 3 algorithms. So there's the gen algorithm, there's the enc algorithm, and there's the dec algorithm, right? So this we already saw. This is how it's specified. There's going to be the key space, the message space, and the ciphertext space. Okay, so these are the 3 spaces that we look at. I already mentioned the notation, right? That we'll write the arrow for encrypting a message, because we expect this encryption algorithm to be randomized, even given k, potentially. Okay, and the decrypt algorithm we expect to be deterministic. So given a C, it should give you one unique answer. It shouldn't give you different answers every time you run it. Okay, so that's sort of the setup. Okay, so now what is the definition, right? So that was the first thing, right? We wanted to have a good definition, and it turns out that the right definition, at least if you're only restricting to like a single ciphertext attack, is the what was it called? Ciphertext only attack, yeah, whatever. You get the idea. Okay, so the definition is that the scheme gen enc dec. Yeah, that's the definition. So we're assuming, right? So for simplicity, we'll assume that the message space is fixed. Okay, so we will not assume that you have variable length messages. So we assume that the message space is fixed, and then so over a message space M, okay, so we'll say, okay, so the scheme in gen enc dec over a message space M is perfectly secret if for all probability distributions, which was the only little thing you were missing in what you were thinking, for all probability distributions over M, and for all messages M in the message space, and for all ciphertext C in the ciphertext space, for which which occur with non-zero probability, such that the probability of C, capital C is C, is strictly greater than 0, is, yeah, let me just write it here because I don't want to erase it. You guys can read here or not? Okay, so probability that the random variable C equals little c, given that the random variable M is M naught, is the same as oh sorry, it's M0 M1. Okay, is the same as the probability that you had the ciphertext equal little c, given that the message was M1. Shoot, I think I messed up. Okay, sorry. I mixed two definitions. Forgive me. I was correct. Forgive me, I messed up. So we want the first one, right, which is that the message M should not depend on the ciphertext. So whether you're given the ciphertext, this is the same as probability that the message capital M was little m. Okay. So what is this capturing? It's saying that regardless of what prior distribution you had on the message space, knowing the ciphertext does not change your distribution. Okay, so it formally captures that the idea that you're not learning anything at all from the ciphertext, because it's not changing your partial information about the messages. Or your information about the messages, there's no partial here. Okay, so that's the idea. Okay, and I'm going to have to skip a lot of proofs, but I will leave you guys with references on where the proofs are, so you can look them up if you're interested. It's instructive to look at them once, but it's not strictly needed for the course. Okay, so that was the first thing. Then we have a nice lemma, which just follows from Bayes' theorem, but says the following. So an encryption scheme, let's use it again. So gen enctech is secure. Okay, so again, over M is secret. You're perfectly secret. Sorry, it's perfectly secret. Did I write if and only if? Okay, this is just the definition. Okay, so this is equivalent, right? Because this is the definition of being perfectly secret. So this condition is essentially equivalent to the following, such that for all probability distributions over M, all messages in M, and for all ciphertexts M0 M1 in M, and for all ciphertexts in C, we have the following. The probability that the ciphertext was little c, given that the message happened to be M0, is the same as the probability that the ciphertext C is little c, given the message was M1. Okay. So in one view, we were mostly concerned about the distribution over the messages, right? So we were saying that an adversary will have some information about the messages, right? And that is unaffected by whatever ciphertext is observed. Here we are flipping it on its head, and we are saying that the distribution over the ciphertexts is identical regardless of which message was encrypted. Okay.
In the definition 1, so we should always be able to decrypt a ciphertext. So the message and ciphertext should be 1-to-1 correspondence, should have, right? So then
I mean for decrypting,
we cannot guess the distribution of message from the distribution of the ciphertext. I mean, this is kind of unintuitive. I mean, if there
Without
exists
the key, basically. If you have the key, then there is a 1-to-1 correspondence.
To keep secret, we don't want to learn anything from the ciphertext.
think of the one-time pad, right? Like that's the easiest example, right? So for every message, so the ciphertext is given by this, right? So if you don't know K, right, and obviously you don't know M because you're trying to recover it, so then C just looks random, right? There's nothing. It's only if you know K that you can recover anything. Yeah. Okay. Any other questions? Okay, good. So this follows from Bayes' theorem. We'll not prove it here. What is important for us is that that one can formulate this further as a game, and it is this approach that we're going to use for the rest of the for the remaining constructions. So these are called games or experiments, whatever. Basically, it's as follows. So there's an adversary. Oh, let's put the challenger first. So there's a challenger, and then there's an adversary. And what the adversary does is picks two messages, M0, M1, from the message space. So I'm giving you the third equivalent definition. Okay, so I gave you two equivalent definitions. Now I'm giving you the third equivalent definition, and the third is the one that we'll use for almost everything else. I'm just intuitively trying to justify what's happening. Okay, so the third definition says what? It says that the adversary picks these messages M0, M1, sends M0, M1 to the challenger. The challenger runs gen, okay, to get a key k, encrypts the key k, encrypts the message that was received. Let's say, yeah, maybe I should have put a sampling. Sorry, picks a random bit b from 0, 1, okay, and then encrypts using the key k the message m sub b, okay, to get some ciphertext c, okay, and then sends the ciphertext c to the adversary. Sorry, not ciphertext. Yeah, ciphertext, and the adversary returns a b guess. Okay, and the challenger accepts if b equals b guess and rejects otherwise. Okay, so that's the game. Okay. Any questions about the game? Is the game clear? Yeah? Okay. And with this game, the definition, so this is an alternate definition of perfect secrecy. So it says an encryption scheme gen enc deck over M is perfectly secret if for all adversaries A it holds that the probability that so let's say this experiment or the challenger outputs 1. Okay, so the challenger accepts given this game is played between, yeah, maybe I should write it in a different way. Yeah, okay, so given A plays, okay, is exactly half. Okay, so that's the definition, and the theorem is that this is equivalent to the first definition, and you can do it through this lemma in between. Okay, because what is happening is that, whether M0 is sent or M1 is sent, right, the distribution over the ciphertext is identical, right, by that lemma. So whatever C is sent, right, the adversary cannot really distinguish them. So the best they can do is just make a guess at random, and that's exactly what it's saying. Because you cannot do much better than this. In fact, you cannot strictly do any better than this. Okay? Good. Okay, so this is the definition. Oh, nice, we have more chalk. Okay. So now let's look at a construction, right, that we saw earlier. So here's a construction. So this is just the one-time pad, right? So the gen algorithm is yeah, okay, maybe I should emphasize this. So suppose the message space M, yeah, okay, so suppose M is given by 0, 1, L, okay, so that's the message space, okay. Then the construction is as follows. So gen is going to do what? So gen is going to sample a k. Yeah, so let's also specify k to be 0, 1, L. So samples a k from the set of all keys. Okay. Enc a given k does what to a message M. So this is going to basically just XOR, right? So you XOR the message M with k, and deck is the same, right? Sorry, C XOR k. Okay, and the claim is that this theorem, you can check, satisfies. So it's called a one-time pad or Werner cipher. I forget. One-time pad. We'll just call it the one-time pad. So theorem, one-time pad is perfectly secure. What was it? Perfectly secret? No, perfectly secret. Yeah. Okay. As per the definition that we had, right? So you basically have a single attack. Yeah, you don't have multiple copies of the ciphertext and so on. Okay. There's also an interesting theorem one can prove, which says that the space of the key has to be at least as large as the space of the message. Otherwise, the kind of things that you were saying. I forget your name. What's your name again? Arnab. Yeah, the kind of things you were saying, right? That you should be able to recover the message, and there has to be a uniform distribution. So for that, from arguments like that, you can show that the key space has to be at least as large as the message space if a construction satisfies perfect secrecy. Okay, otherwise the distribution gets skewed, and then you can detect it.
Just to clarify, like, anytime you say sample something from something, do you mean sample uniformly, or you can use any distribution?
I mean uniformly. Yeah, sorry. So okay, maybe I should specify if it's anything other than uniform. Yeah, maybe I should actually clarify. So the notation that is often used is the following. So if you have a set, okay, and there is a sample element, okay, this would typically be uniform. If there's a process or a distribution, and then you sample element, so then basically you're running the process or you are sampling from that distribution. And sometimes people also write a distribution here as a superscript if you have a set from which you're sampling, and so then you do it according to the distribution. But if nothing is written and you're sampling from a set, it would in general just be uniform. Yeah, it's just a convention. There's nothing deep here, but keeps things a bit more tidy. Yeah, but thank you for the question. Yeah, it's crucial that the k is sampled uniformly, right? Otherwise, otherwise your guessing probability would itself change and so on. So, okay. So the theorem is that if gen enc deck is perfectly secret, okay, then k has to be at least as large as M. Okay. And Shannon actually proves an even stronger characterization, which we'll not do. Essentially shows that all schemes are essentially just a one-time pad that are perfectly secret. Like you can show essentially very strong mapping to this. Okay. So it sort of covers what we can do with the question of achieving perfect secrecy is essentially very well characterized now. Okay. Okay, so the annoying thing about the one-time pad, there are a bunch of annoying things, but one very annoying thing is that you have to have a key which is as large as your message, right? Like which I just said here. So what that means is that if you're downloading a 1 gigabyte movie and you want it to be secure, you need 1 gigabyte of key, right? And that's not very efficient. So this is where this is kind of the motivation for the next chapter, which is, can you relax the notion of security a little bit so that it's still meaningful, and nonetheless it gives us a lot of efficiency in terms of the key lengths that's needed to obtain that security. Okay, so that's the content of the third chapter in the book. It's called private key encryption. And pseudo-randomness. So I'm going to skip a lot of the topics, but we will cover them at some point later, because we'll look at minimal assumptions at some point, and then for that we'll need to revisit all of these things. But for the moment, we're going to follow, so we're going to relax this, right? So we'll follow what is called the computational approach. Okay, so this is again story, so I'm just telling you at a high level. So the computational approach is the following. So we're going to relax the notion of security, so in the following ways. Right, and we do need to relax, right? Because if we don't relax, then we have this theorem that's preventing us to decrease the key size. So we do need to relax. And how do we relax? We start by first saying that security is only preserved against efficient adversaries. Okay. And the second thing we want to say is that adversaries can potentially succeed in the attack. So can potentially succeed with some small, or let's say very small, we'll formalize what this means, with some very small probability. Okay. Okay, something that so we don't have to worry about it in practice. It's so negligibly small. It's like okay, and the notion of an efficient adversary, at least in the book, is PPT, right? So that's probabilistic. How do you spell probabilistic? Probabilistic, is it I? Okay, thank you. Probabilistic polytime. So that's PPT. Okay, and in our case it would be quantum polytime. Yeah. So that's the notion of adversary, and by very small probability we're going to mean the following, that it has to be smaller than inverse poly. Okay, but inverse poly in what? So I'll describe it in just a second. Smaller than 1 by poly. Okay. Okay, so the key thing to understand here is that we are not looking at asymptotics. Okay, we're not looking at, like if I have a 128-bit key, how secure is the scheme? We are not making such statements. We are saying that suppose there is a security parameter, lambda. Okay, so we're going to follow what's called the asymptotic approach to security. Okay, so what the asymptotic approach says is that we'll assume that there is some lambda, which is the security parameter. Okay, So intuitively, you must have seen that when you connect to the internet, it says, it has 128 bits of encryption or 256 bits of encryption and so on. So that's really the security parameter. How many bits, for instance? That's one way of thinking about it. How many bits of key, for example, that you're using? Okay, so that's the security parameter. And what we want to, the kind of statements we want to make are that, so lambda is the number of bits. Okay, so I should also introduce this notation. So this is notation which I also introduced last time. So 1 to the lambda is just 1 repeated lambda many times, right? Okay, so now what we're going to do is we're going to assume that, so if an adversary is a probabilistic polytime machine, right? First of all, you guys are familiar with Turing machines and things, right? Show of hands if you've seen Turing machines before. Not everyone. Okay. So the notion of a Turing machine, at least as far as we are concerned, can be simplified a little bit. So we're going to, there are things called uniform and non-uniform adversaries. We're not going to make the distinction here. So let me give you a simplified version that we need that would suffice. So we will never think about a single algorithm. Okay. So we'll always think about a sequence of algorithms. So for example, if there's a circuit, so if there's an adversary A, okay. So when I write an adversary A, what I'm thinking is that there's really a sequence of A's. So A1, A2, I don't know, say lambda, and so on. Okay. And for every security parameter, there's going to be an adversary. Okay. So if you're thinking of these as circuits, for example, okay. So for length 1, there's a small circuit. For length 2, there's a bigger circuit. For length 3, there's an even bigger circuit, and so on. This is kind of what we're trying to formalize here. Okay. In a Turing machine, these things are kind of automatic because we have a notion. Okay, so if you're thinking about circuits, the input size is fixed, right? It's a circuit. It takes as many inputs as it takes. There's so many wires, right? But a Turing machine is more general, right? Like it has a tape, and it can read the tape, and it can take quite a while to read. And when we're thinking in terms of Turing machines, for every input, we can look at the length of the input and determine how long it takes to run the computation. Okay? And a polytime Turing machine would be one that takes polynomial in the input length time to run. Okay? So those are the two ways of thinking about it. One is this circuit-like thing, where you think for every value of the security parameter, you have a circuit. Or you can think of it in terms of Turing machines, where the only thing that we really need is that it can take inputs of arbitrary lengths. And we restrict to Turing machines that halt in time polynomial of the input length. Is that good? Yeah? For those of you who know, it's kind of clear. For you too, is it intuitively okay? Okay, good. So what we want to now say is the following. Right. Okay, so what we're going to do is all our algorithms. So remember, the algorithm over here was simply saying that the input space is fixed, and you're going to sample from some fixed set. But now this is no longer the case. So all our algorithms, gen, enc, dec, right? In addition to the inputs they were taking, they will take this security parameter as an input. Okay, we will not write it always, but it's implicit. Okay, and what that means is that, and also the adversary. Okay, so the adversary will also always get 1 to the lambda as input, because the security parameter is publicly known, we assume, right? It's like the length of the key, so everyone knows what, like if you're using 256-bit RSA or whatever, so everyone knows what the length of the key is. Okay, and then the assumption we'll make is that this adversary cannot run a computation which is exponential which is super polynomial in lambda. Okay, so the amount of time it takes would be at most some polynomial of lambda to run. Okay, so that's why it's asymptotic. We're not saying that for a fixed value of lambda there is security. We're saying that as you take lambda large and large, as you increase the value of lambda, the larger it gets, the more secure your scheme becomes. Okay? And how do we look at these kinds of scalings? We look at these scalings in these terms. So smaller than poly, so now it should be clear. So it's poly in lambda. Okay? And PPT is already clear because the inputs are going to be in terms of lambda.
So could you remind why do you take unary representation as input here?
Yeah. So the reason is that when you formalize a Turing machine, the notion of a polytime Turing machine is given in terms of the input length. So it's polynomial in input length. And here we want the input length to be easily captured by lambda. So we're just taking a string of length lambda. So you could take 0 lambda many times, you could take 1, whatever symbol you want. It's just out of convenience. Like you could equivalently take 0 to the 0 lambda many times. There's no distinction. If you just write lambda, then storing the number lambda itself takes log many bits, log of lambda bits.
Yeah.
So then it will not run in poly of lambda, it would run poly in log lambda. So that's why you want to just put 1, 1, 1. Is that okay? Very well.
We could have had an exponential Turing machine and had
Yeah, you can adjust the notions. Yeah, you can adjust the notion. So whatever notion of, whatever time you take here, you have to sort of take some inverse of that. And there's some notion of closure that you have to keep in mind as well, because polynomials compose under polynomial multiplication and so on. So it probably would also be the case. But yeah, as long as that is true, you can do it more abstractly. Yes, it is true. Okay. Yeah, so it's a good question. Why polynomials? I think polynomials were chosen because we expect composition of efficient algorithms to be efficient algorithms. So it just essentially comes from this. Yeah, it's not much deeper. Okay, good. And what else? Yeah. Okay. So one thing we wanted to do was to formalize. So these things are called negligible.
What was the reason that you are not taking exponential here?
You can if you want. The reason is basically that you expect efficient algorithms in practice, the way you formalize it, to run in like either you have a linear time algorithm or a quadratic time algorithm, things like this. So people just formalized any power, as long as you can run it as some power of polynomial, I'll call it efficient, even though that's not necessarily true. Like if it takes, I don't know.
I'm asking what this is smaller than 1 over poly.
Yeah, so this is related to the fact that if you have an event that happens with 1 by poly probability, and you're an efficient machine, you can repeat it poly many times and observe it with some constant probability, right? So if it's strictly less than 1 by poly, then regardless of how many times you repeat, as long as you're efficient, you would not be able to actually observe the event.
So it's enough to take 1 over poly instead of exponential.
Yeah, it's enough to take 1 by poly. You could take inverse exponential, that works, but it could be slightly bigger than inverse exponential, and you would still not be able to have the event happen with any meaningful probability in real life.
But there is a gap between
Inverse exponential and 1 by poly, yeah. That was, I was going to give you some examples. Yeah. Okay? All good? Okay. So I'm going to erase this part because, or maybe let's erase this. Yeah, let's erase this, okay. Yikes, sorry. Okay, so now we have a definition of what is a negligible function. It's basically just that, but it's stated more formally, which is also good to know. So a function f is negligible if for all polynomials p there exists an n such that for all little n greater than capital N, it holds that fn is strictly less than 1 by poly n. Sorry, you could also take lambda. It's just it's used to denote the same thing. Okay, so what is this saying? It's saying that, since we are concerned about asymptotics, right? We don't care. It could be that for smaller values of lambda, your function is large, but it should always be the case that after some cutoff, which in this case is capital lambda or capital N, the function becomes strictly smaller than any inverse polynomial. Okay. Like for example, if you had a step function, not a step function, whatever, a discontinuous function, say it was like 1, and then after this point it goes e to the minus n. Okay, this would still be negligible because as you increase n, it decays. Okay, so it doesn't matter what it does in the beginning. There has to just be a cutoff. That's the important part. Okay, and intuitively what this means is that we're just saying that in practice the scheme will be secure for a large enough lambda. That's all that it's saying, because it doesn't make sense to stick to any fixed lambda, right? Because of course in practice you would, but it just means that as technology improves you should be able to just increase the lambda and your security would improve. That's kind of the idea behind asymptotic. Okay, and then some examples of functions that are negligible. So example 3.6 from the text. So these functions 2 to the minus n, 2 to the minus root n, n to the minus log n are all negligible. Okay, so yeah, I'm not doing the proof. I actually did not even check it for myself, but it's good to do it once to get your hands dirty and see what is and isn't negligible. Here is a useful proposition which is easy to see. So suppose negl 1 and negl 2 are negligible functions. Okay, then we have the following. So then negl 3 defined as negl 1 plus negl 2 is also negligible. Okay, and then essentially a corollary of this is for any positive poly P, negl 4 defined as P times negl 1 is also negligible. Okay. Oh, sorry. It essentially follows from the definition. Because it's good to know. Basically, it's saying that negligible essentially stays negligible under compositions of the sense that additive compositions. Okay. Of course, if you add exponentially many negligibles, then it would become non-negligible. But the point is that no efficient algorithm can, make the event corresponding to negl happen exponentially many times. Right? It can at most do it poly many times, and that would still be a negligible function. So you don't gain anything. Okay, so that's why the notion sort of makes sense. Okay. Okay, good. So now section 3.2, definition of computationally secure encryption. Definition of Okay, so what's the definition? So we'll say that gen enc tech oh, this is just defining an encryption scheme. Okay. So definition 3.8. We'll first define what we mean by a private key encryption scheme. So private key encryption scheme is a tuple of algorithms, right? Oh shoot, algorithms. Gen enc tech such that the key gen algorithm, so gen takes as input the security parameter and produces a k. Okay, and they'll assume without loss of generality that the length of k is at least as much as lambda. Okay, I am going to mix lambda and n because the book is using n, and in my head I always use lambda. So, so yeah, lambda equals n. Okay, don't get confused. The second is encryption. Okay, so the encrypt algorithm is going to take as input a message m, right? So this is exactly the same as we had before. So you have k and m, it'll produce a c. And decrypt is, unsurprisingly, decrypt k given c. Okay. And the fact that there's lambda dependence is already captured in the fact that the length of the key is going to be at least lambda. Okay, so all algorithms are going to be intuitively polytime. And I kind of forgot a tuple of I wanted to say PPT algorithms, right? So that's kind of the key distinction. Everything else is essentially the same as before. So these are PPT algorithms. Okay, so this is the new part, and this is the new part, and this is the new part. Okay, everything else is essentially the same as we had before. Okay, and you require the correctness condition, so you require that decryption of encryption of m gives you m. Okay. Okay, and the security game now is going to be exactly the same as what we had before, except that the adversary would now be polytime, okay, and the probability would be half plus negligible instead of half. Those are the only two differences. Okay, so let me write it here maybe. So security is again using the game. Same as before, except one, adversary is PPT, and two, should not succeed with probability greater than half plus negligible. Or rather, maybe I should say, yeah, let me not write the negation. So adversary succeeds with at most, succeeds with probability at most half plus negligible. I think it's better because contrapositives can get a bit more tricky. Okay. Is that okay? I have 1 minute left, and in this last 1 minute, what I'll do is I'll give you the definition of. Okay, so far we looked at the definition with. I don't.
Any leak loop, but what I'm saying is class seems 5 minutes before
Okay. Sorry. Okay, yeah. So we'll do CPS security next time then. So far it's a good point to stop actually, because we kind of started with the information theoretic notion, right, and we ended with what the asymptotic security notion of security would be. Okay, perfect. Okay, thank you.